Okay, yesterday we had done through the chemical equilibrium part there. The only bit left over was the analysis with respect to Gibbs free energy and its relationship with respect to equilibrium. But I think I had given a few hints in that particular process there already as to where they will connect. They will be connecting in the chapter electrochemistry predominantly, and electrochemistry needs and requires ionic equilibrium. So let's push through ionic first. I'm guessing electrochemistry is going to be starting off in your school sometime soon. After organic is done, they'll push through. They have not done electrochemistry yet, na? Or is it completed already?
No, sir. No, it's not done, sir.
Not done. Okay. So I suppose maybe one or two chapters in physical chemistry are still left over. Okay. Is that sound on your end or on my end, right?
Sir,
That car honking.
it's on my side, I think, sir.
Okay, alright, huh? Because I could hear a weird echo on my side also. I was not sure where it was coming from. Could have been mine also. Okay, let's start off with ionic equilibrium. So the simple idea here is when you're going to be looking at equilibrium in solutions, that's a much more larger domain. So we end up having a separate chapter for it effectively. It is part of the same chapter in your NCRT though. I have a recommendation here for you. There are a few golden nuggets in NCRT. When I say golden nuggets, I mean things like information, not theoretical understanding type of knowledge, but theoretical factual type of data, which is going to be very useful in solving other chapter questions. One such piece is available in your chemical equilibrium chapter in NCRT of class 11. So when you are going through this chapter, I recommend you just skim through the NCRT once, not for any understanding part, but for any data, factual data type of thing which is available. There was a JEE advanced question. This was like I think 4 years or 5 years back, maybe 6 years. I don't know, five-ish years back, 4 to 6 years basically. So where this was a question on coordination compounds. It was a more than one answer correct type of question. I think that year's paper probably contained either you get full marks or you get negative, something like that, or maybe it had partial marking. I'm not sure exactly about the exact marking scheme at that time. Good chance it might have been full marks. The question was involving, I'm not sure which one over there. I think it was either copper 2 plus or nickel 2 plus. I'm not 100% sure right now. Even I have to go back and check that data once. Where it forms two different types of complexes. One which is going to be, of course, yeah, if it has to form two different types of complexes, there's going to be two possibilities. One which is going to be having 4, coordinate covalent bonds, another which is going to be having 6 coordinate covalent bonds. Complex law, what is going to be happening is you're going to be having a central metal atom or an ion or something else. Instead of a metal, it can be a non-metal also in some cases, where you end up having one or more coordinate covalent bond being present, which is going to be basically connected to the central system, and depending on how many it is, you end up having different structures being possible according to standard VBT. So you're going to be having 4 or 6 being the possibilities over there, and depending on the temperature, you end up having it shifting from one to the other. I think it was for nickel 2 plus. I'm not sure why I'm thinking it is copper 2 plus. Probably because my stupid feeling tells me it may be copper also, but I think it was nickel more. So that particular information, that temperature shift when it is happening, is around 0 degrees Celsius in acidic medium in HCl. This information was given in a chemical equilibrium NCRT textbook piece over there. When I say information, it is just mentioned that there is this equilibrium possible, this color change happens, and this geometry change happens. Or I think they have not mentioned geometry change, they have mentioned only color change there. But they have mentioned the formula of change over there. So when you link it up with coordination compounds chapter and make that into a question, that becomes a very, very high level question where it is exception based, but the exception is properly given in the NCRT textbook in a place where students normally do not pay attention to it. So that is the interesting part over there. So NCRT textbook, yeah, for physical chemistry it is not that particularly useful, but for all the chapters which are done, 11 standard chapters, when you feel you have gone through it once, look through them for these kind of special pieces of information. These special pieces of information can help you solve a lot of really complicated questions when they do show up in JEE Advanced. Because ultimately, JEE Advanced also does not like the coaching industry. So they also prefer that the students are on a more even platform. The entire country wants that to an extent, but the coaching industry obviously destabilizes that platform. So effectively, they also prefer that if they are asking any exceptions, they would prefer to ask it from the NCRT and not outside of the NCRT. Have you seen this piece of information which I am talking about before?
No, sir.
Go check it out. It is there in chemical equilibrium. It is there in, I think, Le Chatelier's principle, temperature dependence. So this is there under Le Chatelier in the NCRT textbook under, I think, temperature dependence. I am not 100% sure if it is been removed or not from the NCRT now, but I remember chemical equilibrium is still there, so they should not have removed it. Okay, so this is the kind of connection which you can make from other chapters using NCRT. So pay attention to them. No need to read the NCRT for physical chemistry thoroughly and that kind of nonsense. Pay attention to these kinds of small nuggets of gold which are randomly buried there and mine them as necessary. Mine them, now mark them in the NCRT or write it down as a separate point. This is the only piece of information you're going to read through once more when you're revising the NCRT. Everything else you know for a fact, you already understand. Understanding is sufficient. Physical chemistry parts. Okay, ionic equilibrium, let's start off over here. Alright, so let's start off from the standard part where things start off from acids and bases. Now I'm assuming you have a decent idea as to what acids and bases are, but I'm just going to give you the ionic equilibrium blast through which is necessary here. There are three standard definitions: Arrhenius, Bronsted and Lowry, and Lewis. Now the idea here is very simply this: you're going to be having the older the definition, the weaker the definition, the smaller the boundary of the definition. As scientists basically started understanding what they were studying more and more better, they started coming up with more refined definitions. And as more refined definitions came about, obviously the newer definition should include the entire boundary of the older definition and increase its scope and understanding. Only then is it to be considered a newer definition. So by default, Bronsted and Lowry was designed to completely look into the scope of Arrhenius and give a new explanation for it. It's like, how to say, Newton's way of understanding gravity and Einstein's new space-time fabric, that way of understanding gravity. So effectively what happens is, Newton's way of understanding gravity mathematically is perfectly correct. He couldn't explain why the force acted over a distance, but the entire mathematics of it and the entire domain of it was beautiful. And Newton is the greatest, scientist of all time. Theoretical by a huge margin, I mean including Einstein. Simply because that dude basically did too much work. Calculus is just nothing comes close to calculus, sincerely. And yeah. So simply put, what did Einstein's theory of gravity do? It basically understood that Newton's was perfectly correct. So any theory of gravity which he came up with had to include and explain how Newton's worked, expand the scope of its understanding, and at the same time help in solving cases where Newton's was failing. One of the places was where Newton's law of gravity, I would not say fail, it doesn't work perfectly. You can add Einstein's adjustments into it and mathematically make it work better. The idea there is, when you're looking at do you know what I'm talking about? Do you know an example where Newton's theory of gravitation doesn't work? You've done gravitation in your school, na?
Yes, sir.
Where do you think it doesn't work?
Satellite function.
No, this is fairly, it's not about mathematically looking at it. Yes, mathematically looking at it will give you some ideas, but mathematically when you're looking at it, you need to really understand the core principle behind it. Only then it'll click out. Einstein did that only basically. And then he came up with the space-time fabric. Newton's law of gravitation works on all the physical scales which we can logically imagine. Only when the physical scale becomes awkwardly broken do you end up having a problem. So obviously Newton's law of gravity is not something which extends into a much more smaller domain. We don't have atoms and molecules really getting involved with gravity over there, or the way in which it works is going to be obviously different. Another domain where it doesn't work is going to be when the objects which are in the other boundary end. See, effectively any theory has a boundary. Correct. What is a theory? A theory is going to be some logical mental framework which you take, then you apply the rules of mathematics on it to make a full domain. Once you apply the rules of mathematics with an imaginary picture, then automatically that becomes physics. Till you have just, if you have only a mental image, and that mental image is not having perfect rules of physics being completely applicable, or you have your own set of rules which don't feel mathematical, or which have a mathematical aspect but are not completely mathematical, that falls into the domain of chemistry. Basically chemistry is what are you learning? You are basically learning mechanisms and pathways by which a reaction may proceed through. Yeah, how do we know it may proceed through it? What do we mean by we have proved it? We have taken photos of it, but we know that at that level Heisenberg's uncertainty principle absolutely applies. So taking a photo means we are observing it. The act of observation changes the experiment definitely. So ultimately we can only be like reasonably sure for whatever we are proposing as a mechanism. There are always alternate pathways, there are always weirder things, till we can take a closer snapshot in a more meaningful manner by being less obtrusive, less observant. It is going to be much more complicated to get definitive proof. We have already reached that domain predominantly, and our technology is already at a stage where we are breaking that Heisenberg's uncertainty principle too much. So we don't trust what we see predominantly anymore, because we can force what we see into becoming true. Anyway, that is a different domain there, but what I'm trying to explain is chemistry is predominantly going to be something where we have mathematical foundation, we collect information mathematically, then we make a mental picture of it and we try to make up our own rules. Once we have our own understanding of rules and patterns which we have observed based on the mathematical data we have collected, then we come to the next stage of understanding, actually codifying those rules into physics. Once we are able to codify it into a proper mathematical framework, yes, technically we can call it physics. That's why when you look at quantum realm, there is no quantum physics or quantum chemistry. Both are basically the same. It's more efficiently called quantum mechanics. So yeah, mechanics in the sense, mechanics helps you understand that it is supposed to have a proper framework of rules which have been codified, which have been properly understood, and these rules have to be followed properly over here. And because you have a codified set of rules, it obviously comes into the domain of physics. Till it has a perfect set of rules which can be run mathematically, we don't put it into physics. So effectively the idea here is when you're going to be looking at the boundary conditions at which a particular physics system fails, you have to look at what boundary condition it works in. It is basically a mass-based conditionality, correct? Gm1 m2 by r. It's a mass-based and distance-based conditionality. That's what gravity is. So gravity's boundaries are going to be extremely heavy mass or extremely low mass, and simultaneously smaller distance, larger distance. Larger distance, we know the force becomes much weaker, so we can throw it out. That is not going to be a boundary condition because that extends to 0. It doesn't extend to any particular number. So the problem comes when it extends to some particular number. One of the reasons why we don't care about gravity at quantum levels is because the mass extends to very low values. So in that boundary also, it technically extends to a 0. Do you understand what I mean by extending to a 0 and extending to infinity on the other direction?
Yes, sir.
So the idea here is, mathematically speaking, when you're going to be having bounds, you have learned limits, correct? Limits which extend to 0 are perfectly fine to throw them as a 0 because we think we have a reasonable understanding of a 0. But the truth is 0 and infinity are the two opposite ends. it is very very rarely minus infinity and plus infinity, because minus and plus basically come to a convergence at 0. So the two boundaries of the universe in a sense are 0 and infinity actually most of the times in terms of mathematical functions. So when you're going to be having 0 as one of the boundaries over here, what happens is this 0 is going to be something which we can generally not bother about. We can say that is understandable. Infinity though is not particularly understandable. So when you're going to be having, what to say, two very heavy objects where the distance also becomes much lower, you end up having problems associated with it, or you end up seeing a boundary being there. So mathematically the rules will now have to change. Do you understand what I am hinting to over here? Take a guess, what would be the conditionality which breaks Newton's, which we could have observed in our patch of the universe? Because ultimately we have to collect data, na? Till we collect data, we don't know if it's being broken. So what is the data which we could have collected about where Newton's probably doesn't work? And Einstein had to step in and explain. Two very heavy objects at closest possible distance. Only then gm1 m2 by r squared will basically end up showing some funny business, and gm1 m2 by r will also show some crazy business there. So what is the heaviest object which we can observe?
The sun.
Correct, exactly. What is closest to that damn thing which is reasonably heavy? You should not call it damn
The
thing, but
first
what is
planet.
closest to that beautiful thing which is reasonably heavy?
The closest planet.
Which is that?
Um,
Seriously? So Mercury is your closest planet in the solar system, the closest real reasonably large size object in the solar system. So this object over here is going to be something which is going to be having a slightly wobbly orbit. It is following Newton's orbit, but it wobbles in that orbit slightly. So it changes that orbit tiny bits here and there. Those particular changes are happening because gm1 m2 by r and gm1 m2 by r squared are going crazy high over there, and those wobbles are basically causing shakes over there. This was not something which could be explained, or this was the deviation of Newton's theory of gravity which we could actually observe. Effectively, you can predict where the boundary should be. All you have to do is think, what does the boundary mean? Where will problems happen? Scientists do this actually. What they do is they basically try to understand whatever they are trying to study further in a mathematical fashion, then try to understand what is the boundary associated with that mathematical function limits wise, mathematically speaking, then try to see where those boundary conditions tend towards infinity, which is going to be at a reasonable distance still, by which we can measure using light speed, because light speed brings that infinity closer to us. So if it is reasonably close from a light point of view, we will be able to measure information about it and collect data about it, which will help us see what is the rule at that boundary. How is our mathematical depiction of it holding good, or if it is breaking, even better. That means we get deeper understanding. So effectively, this is something which was explained using Einstein's theory of gravity when he proposed that space-time fabric is bent by mass. Automatically that bend was having a slight extra kink. You know, a bend is never a straight line function or a nice simple function. So if it's going to be a bend, it is going to be a nice function like this. So when it is going to be a function of this sort over here, you will have, possibilities of the mathematics over there being slightly more complicated at the edges over there. So that was able to be explained using Einstein's gravity over there, which basically added extra layers to Newton's mathematical definition of gravity. That is what it did. So same logic applies in every goddamn place where you are basically doing chemistry. Chemistry is about understanding more and more deeper, connecting with physics, and then reaching a domain of physics if we can reach it. Or accept our shit will not work here with physics perfectly, and we'll have to go into a domain of biology or material science or whatever it is, some other domain. Anyway, coming back to things over here. So each of these three definitions of acids and bases are going to be necessarily explaining each other on top of the other over here. So let's talk about Arrhenius over here. Arrhenius is the most simple definition over here. So Arrhenius definition basically did not even define them as acid and base. It defined them as acid and alkali. Yes, the alkali became a base when we are going to be considering the later definitions. So how was this defined? This was defined by on very simple analysis over there. You're going to be having touch and taste is basically what they used to define this. So when you're going to be looking at acid and alkali here, acid donates H plus in solution with water. This is going to be a key definition to be paying attention to. And alkali donates OH minus in solution with water again. So this is the definition with respect to Arrhenius over here. Now, Bronsted and Lowry definition effectively defined this into perfect opposites over here. Bronsted and Lowry definition of acid is going to be the exact same thing. It donates a H plus. But if it has to be a perfect opposite, how it defined was, it defined a base now. It did not call it as an alkali anymore. A base is something which accepts a H plus. Donates opposite is going to be accepting, so accepts H plus in solution with water. Now, this is going to be a Bronsted and Lowry definition. Lastly, we are going to be having Lewis definition, which is going to be superseding all of these two over here. So, in the Lewis definition over here, we are going to be studying how the base accepts the H plus more carefully. So, when it comes to the Bronsted and Lowry definition of this over here, this is the real change. So, in this change here, how do we define it? OH minus is the typical example, which is to be obviously explained away because OH minus is what was defined by Arrhenius over there as a base or alkali. So OH minus structure is very straightforward. Oxygen is going to be having 3 lone pairs present with a negative charge. So the H plus will basically be coming and attacking a lone pair. And in this process over here, you're going to be having the OH minus donating a lone pair and accepting the H plus. So the base accepts the H plus by donating a lone pair. Hence accepts. So the way any base is going to be accepting H plus is actually by donating a pair of electrons to it. So this was basically the next stage of the definition which Lewis basically went into. He defined base first because he had understood base here properly from the definition with respect to OH minus. A base is capable of donating a pair of electrons. So this is basically going to be something which is going to be defined as a base. The pair of electrons here, of course, can be anything. If you're including organic chemistry ideas over here, the pair of electrons can include lone pairs, it can include pi bonds, it can include pi clouds. All of them are basically accepted over here. So pi bonds also work, or you can say p clouds. P clouds usually includes, or rather usually is understood as lone pairs and pi clouds. So pi clouds here basically are going to be all your aromatic systems and your regular pi conjugated systems or simple pi bonds which are having good amount of electron density associated with them. So all of these are basically capable of donating a lone pair. Now if this is going to be the definition, in the previous definition itself, Bronsted and Lowry had properly defined acid and base as opposites of each other. So the definitions have to be opposites of each other also, because this is now another constraint which this guy has brought in. So when you're going to be having these to be opposites of each other, so if you're going to be having them as opposites, how it works out is you're going to be having the next definition also having to be opposite. So this is donates a pair of electrons. So the opposite to this is going to be accepts a pair of electrons. So what is necessary for this over here? For it to accept a pair of electrons, empty orbitals are the key thing. So you can think of it as empty valence or orbitals or empty bonding orbitals. Bonding capable orbitals. Now, I am using an awkward term over here, an orbital. How do we define an orbital? Why I want you to pay attention to this, because you had mentioned chemical bonding MOT is also something which no, I don't remember you mentioning that actually. Or did you mention chemical bonding MOT is a problem?
Yes, sir.
Okay, so my memory is still decent only. temporary memory, but still it is still decent. So effectively, I had mentioned chemical bonding MOT is a problem. So MOT needs you to understand orbitals a little bit in a refined manner. So I'll just give you the definition now, since I'm anyway touching upon it and it will be useful here. So when it comes to an orbital, think of it as, let me give you a definition over here as to what we are trying to do here in orbitals. We are trying to define space mathematically. Because ideally speaking, the problem is space is something which has to be defined now if we have to understand it. So defining space is a very, very complicated and tricky process. Why is because to define anything, we need to study it and then come up with something associated with it mathematically. Because otherwise we can't do anything mathematically. We can't really come up with any mathematics if we are not studying or observing something. But how do we understand space? Space is nothing in our brain. So the most, non-intrusive way. So ultimately, scientists and everybody understood Heisenberg's uncertainty principle is something which you cannot violate. Alright. So when we are studying something, if we throw more of something which will disturb it to study it mathematically, our data will be worse. What is the smallest thing which we know how to observe and collect information about? That is, smallest thing is going to be the electron. We obviously can trap neutrinos and other things which are smaller than electrons now. We have mathematically defined quarks, up, down, a full set of tiny particles we have now defined. But the reality is observing them on scale and collecting information on scale to be able to make up initial fundamental theories, we are still not able to do. So one of the ideal ways which we had found at the earliest point of time to define or to understand space mathematically was throw an electron into it and define the space that electron is going to be observable in. And mathematically you can define the electron because that is going to be something which is going to be observable still. So define the space based on that electron, that becomes your definition of space. So that is basically how we started defining space mathematically. Basically, we threw the smallest object we could observe effectively to some extent or the other, or to come up with some mathematics which were reliable for it at that level. And we started calling it or thinking of it as space, because that was the way to define it. So when it comes to defining space, how is space defined? If I'm looking at the space between my hands over here, this space, I can't define it as just this region. We have to define space as total minus everything else is this region. That is the unfortunate way of defining space, because we don't understand any one part individually. We don't understand how it's connected to everything else. So we have to define it from the point of view of I'm observing this. So this is everything minus everything else is this. That is effectively how we end up defining space predominantly. So when we define space, we are going to be defining space mathematically, meaning in the form of equations or functions. You can think of it as whichever way you want to call it. These mathematical functions are effectively what are called as orbitals. So how do we define this orbital over here? We throw an electron into that space. We say that, okay, the electron is technically an unbound entity. Why are we capable of using the electron effectively to define space? Because it also works like space. In the sense, it extends into infinity. The probability of finding an electron, which is supposed to be in an atom over here, in some random location in Spain, is not zero. In some random location in a foreign country, in a random location outside the planet Earth, is still not zero. So the idea here is, you can always have the probability of finding an electron which is supposed to be inside an atom at some other location. Why so? Because at some point of time that atom was formed. There is a probability that the electron was in some other location before it got formed. So that probability is also being added in, because we are measuring the probability of finding the electron over all time. So if we are adding all time over there, technically there is always a chance. Probably in the future when we are breaking that particular atom out, maybe for whatever reason, or it breaks down, maybe the electron will be thrown away in some other point over there also. So technically the probability of finding an electron at any random location of any individual atom is never going to be zero. It's never going to hit zero. So that feels like an infinity function, just like space. That is one of the reasons why we could map it with that. So orbitals, how we define it is, we define an orbital as the space where probability of finding the electron is maximum. Correct. That is how we define it in atomic structure. So when you're going to be defining an orbital, we say that probability of finding electron is maximum in that space. Now when we say it is going to be maximum in that particular space, what is the real idea behind it? We define a boundary condition for maximum. That mathematics is the boundary idea there. So when you're going to be defining it as maximum, different books, different places will give you different diagrams. NCRT, I think it gives you 95% or 90%. I do not remember which one NCRT gives you. But different books, more detailed books will want to show off that they have calculated more. More detailed scientists will want to show that off definitely. That is how science works. So basically there will be different higher level textbooks giving you more detailed diagrams for each of those things. Ultimately, why detailed diagrams are important? Because detailed diagrams are basically able to give you a calculation closer to a boundary. If you are able to make calculation closer to a boundary, there is going to be a good chance a newer theory can come to explain that away in a more beautiful manner. If it comes, that will expand the scope of that particular science itself, and it will be a massive leap. So basically, those are critical things. That's why calculating information about the boundaries are very important. So we generally bound that space where probability of finding the electron is totally 90 to 95%. When it is totally 90 to 95%, we say, okay, this is sufficient enough of a definition. We don't need to care beyond this. And that is what we define as an orbital. That is where we basically get shapes of orbitals, etc. But there is going to be a slight difference when you're going to be trying to study something which exists already and something where you can study the formation of it, study formation of something. So when we are going to be considering atoms are considered as basic building blocks. They are going to be automatically anyway existing. Atomic force is based on nuclear attraction, nuclear forces of domain over there. That is not in the electric domain or the electron domain over there. So something which exists already are atoms. But something which we can study are bonds and formation of bonds. Obviously, the simplest things which we can study are molecules which are diatomic, because those are the simplest bonds. So where did scientists go from here? So they basically defined space as that 90 to 95% area bound where probability is maximum. That was for the atoms level there. So that was for the atoms level there. Damn it, sorry. I keep a bunch of alarms normally. There is another alarm about to ring. Okay. So, first off, what was the experiment of defining space? Scientists went into atoms. They defined space based on maximum probability of finding an electron in that location. Okay, that gave them a way to mathematically get an equation for space. Obviously, once they got an equation for space, they don't need the electron anymore. They can now theoretically map things out because the electron is a wave function. You can study that wave function mathematically. So the atoms here, that definition basically defines one bound unit of space, one bound defined unit of space. Now, when you are having bonds and formation of bonds, now you have to do everything mathematically and then see if your mathematics is proven by experimental data. That is the next step. This is going to be prediction stage here. So bonds and formation of bonds, especially for diatomic molecules, scientists came up with a new technique, which was your molecular orbital theory. They now had another way of defining space, where they are now creating spaces. How are they creating spaces? They are creating spaces based on the same way in which I explained what space is to be defined as. One is space within a particular boundary, and everything else which is not in that particular boundary. That is the way to define space. So effectively they now came up with a new way of defining space: bonding molecular orbitals and anti-bonding molecular orbitals. So when you are combining spaces, when you are attaching electrons into a new space, you are combining spaces there, correct? So when you're combining spaces over here, forming bonds can be thought of as combination of spaces. So when you're combining spaces here, you have to understand it mathematically and come up with a deeper model for it. So that model is basically molecular orbital theory, where when you are talking about combining two spaces which are already defined spaces, remember atoms are already defined spaces. So you are combining these two defined spaces, so you have to now come up with a new space. That new space they came up with, mathematically speaking, was something they had to define newly, because it was a new space. How they defined that new space was, okay, I can define spaces this region and everything else. I have to now combine it with the universal equation over there. So if I want to define this region, it will be everything else, or the total minus everything else will be this region. That is basically how we define that space. That is technically going to be the bonding molecular orbital. And they basically refined the combination of space equation for the electron into maximum probability in that space. So this space bound by my hands, you now look at where 90 to 95% probability is going to be present for finding the electron in that space. That effectively becomes bonding molecular orbital. 90 to 95% probability of finding electron in that space. So that is going to be your bonding molecular orbital understanding. That is how they define that. Obviously, anti-bonding molecular orbital is also a defined space. So if it is to be a defined space properly, you'll have to now throw an electron into it. You have to define that space perfectly. Now you have to throw an electron into it, calculate the mathematical boundary it is going to be defining according to the information which you can collect for the electron, or information you can calculate for the electron effectively. Because electron is already a defined equation, so you throw it in, you can calculate for it if it is simple enough. So that is going to be defined as your anti-bonding molecular orbital here. What is this equation going to be? This is going to be locating electron in ABMO space where we have 90 to 95% probability of finding electron in that space. So this is basically what is going to be the definition of bonding molecular orbital and anti-bonding molecular orbital. That is why they are defined as a pair. In a sense, bonding molecular orbital conceptualizes that the space between the atoms should have very high chance of finding the electron which is going to be bonded. And the non-bonded electron, if the electron is not going to be involved in bonding, it should not be in the space between the atoms. So if it is between the atoms, you are going to be looking for the mathematical equation of the electrons which are going to be bonded and connecting those equations specifically, which results in your bonding molecular orbital mathematical equation which you will arrive for it. Anti-bonding molecular orbital is going to be another mathematical equation which gives you again highest probability of finding electron in that non-bonded space, which is technically everything else. So that is the idea behind orbitals and this over here. I have already gone unnecessarily into random nonsense there when I was doing Lewis. So I'm going to come back to this. We'll go back to molecular orbital theory when we are discussing MOT on a later date, when I'm giving you a chemical bonding blast through maybe. So for now, we'll come back to Lewis acid and Lewis concept over here. So Lewis concept is basically you're going to be having a Lewis acid being something which is going to be capable of accepting a pair of electrons, which means empty bonding capable orbitals are to be necessary there. Bonding capable, they can be anti-bonding or bonding. Because what is the definition of anti-bonding and bonding? That is basically something which comes up from the space of interaction between two atoms. If a new atom is coming to interact, obviously the original system space would have been called an anti-bonding, but that will now become a bonding. because if it is going to be interacting with another atom, that will be bonding in that location but anti-bonding with respect to this. In a sense, if I am going to be having, say, A and B having a bond over here in this direction, in this space here, this space is going to be called as bonding molecular orbital space. That is, this region between them is going to be called BMO space. Whatever that space is going to be, however big that is, however, it doesn't matter. So this is BMO space with respect to AB. Let's say there is going to be a C which is now interested in attaching itself to A over here. So this space is technically going to be anti-bonding molecular orbital space. I should put it in white over there, sorry. So this space is technically going to be anti-bonding molecular orbital space with respect to AB again. But it becomes bonding molecular orbital space with respect to AC after formation of bond. Why am I teaching this part now specifically? Have you started noticing this in your organic chemistry? You are doing organic in school and you do it at a good detail there. Sometimes they will mention to you that, let's say I'm looking at something like this, undergoing, say, electrophilic addition. You are familiar with this undergoing electrophilic addition, correct?
Yes, sir.
So in this here, have you been given an orbital description of it by any teacher so far? I'm curious.
No, sir.
Okay, alright. Then I'm not going to poke into it right now. When I discuss this, we'll discuss it. Effectively, the idea there is you will have attacks usually happening of the electrophile from an anti-bonding location, not from a bonding location. Same thing for, let's say I'm looking at SN1. Not SN1, SN2 is most effectively looked at. SN2, what's going to be happening? SN2, you're going to be having a carbon. You're having 3 fellows like this. And you will have one of the bonds which is going to be leaving. This is going to be leaving group. This is going to be attacking nucleophile. Correct?
Yes, sir.
Typical SN2's transition state is supposed to be understood like this, yes?
Yes, sir.
So when you're going to be considering this over here, how they define the attack location of the nucleophile is, this is supposed to be attack from anti-bonding space. So if you look at deeper textbooks, like say, or revision time, maybe they'll give you this, or I'm not sure. Usually this nonsense used to be taught earlier, but advanced level also is now more interesting. They have learned new tricks. So yeah, they have become better. They are not wasting time on unnecessary nonsense like this. But internal exams, once in a while in revision, you might come across some statements given like that, more than one answer correct question especially. Just random information for now. If I am interested in discussing it, if we get to that type of thing sometime later, I'll have a discussion on that some other time. For now, no need of touching on this, but just information for now. Technically, the attacking nucleophile attacks from the anti-bonding molecular orbital space with respect to which one? Any space you have to define with respect to a bond. With respect to which bond? In this case, what do we say the attack is like? We say it is opposite side attack. Correct? That is what we say. Yes or no?
Yes, sir.
That is why you are going to be having inversion happening. Correct?
Yes, sir.
If you are going to be having chirality at that location, at this carbon here, for whatever reason, if it is chiral, we have an inversion happening there. So why does that happen? Because it is happening from opposite side. What does opposite side mean? Opposite side means it attacks from the anti-bonding molecular orbital space with respect to leaving group. That's all. whatever bond the central fellow had with the leaving group, with respect to that bond, this is the anti-bonding molecular orbital space. That's the idea here. Anyway, that is just random information. You will be probably getting this information showing up only in your internal exams in very complicated papers. So I am now going to get out of this completely and get into ionic again. Enough of orbital bullshit. That has its own time and place. Okay, so let's continue on to ionic equilibrium in full mode now. So Lewis theory is going to be a larger scape. So this can be considered as Lewis. Bronsted and Lowry is going to be a smaller box inside it. And lastly, Arrhenius is going to be the smallest box inside both of them. So this is going to be your set theory way of looking at all three of these over here. Now let's start off with proper mathematics of ionic equilibrium. So when it comes to mathematics of ionic equilibrium here, let's start discussing with the basics over here, water. Because everything is going to be acting as an acid and a base in water. So what does it mean? Why water specifically? Because water is your universal solvent, obviously. Why is it a universal solvent? Mainly because it is available everywhere and every scientist could collect information about it. Secondly, it dissolves most things. Most ionic things dissolve in it. Decent number of covalent substances also dissolve in it because of hydrogen bonding. One more reason is because it acts as both acid and base. So we can try to understand it from an acid and base perspective simultaneously. So before we study water, let's now define acid and base mathematically a little bit more carefully and proceed on with it. So let's say I'm going to be defining strong acid and weak acid specifically now. Let's say from a strong acid perspective, we are going to be using water as the balancer here because we are now testing only with water. Strong acid dissociates 100% in water. Weak acid does not dissociate fully. That is the basic definition which we are going to be going with. We can of course refine this definition a little bit more mathematically, but we will stay at this level for now. So when you're going to be having it dissociates 100% in water and this guy doesn't dissociate fully over here, let's try to understand this doesn't dissociate fully here. Because this dissociates 100% is like a 0 point. In a sense, it is not going to be giving me more information at this stage of observing. So we'll have to study the next boundary which is more meaningful in a more easier manner by collecting more information. So that boundary we study is the weak acid part over here. So when you are studying the weak acid here, let's now consider a weak acid and define it. We'll take a sample weak acid HA. Acetic acid you can take. Acetic acid is going to be having CH3COH, of course is a formula there. So HA is going to be reacting with water as an acid. So when it behaves with water as an acid, what is going to be happening? We'll be following everywhere Bronsted and Lowry definition when it comes to ionic equilibrium, because this was the easiest one to calculate information about and calculate data about. So massive amount of data was collected based on Bronsted and Lowry, H plus and its complements calculations over there. So when the HA ends up behaving as an acid in water, what is going to be happening? You're going to be having the water behaving as a base. So it will accept the H plus from HA to become H3O plus. And it will produce an A minus, that is HA will produce an A minus in the process. Okay, so this is going to be the expression we are going to be studying right now. So if this is the expression we are going to be studying, we can now have a K equilibrium associated with it. This K equilibrium is going to be, of course, concentration of H3O plus into concentration of A minus divided by concentration of HA into concentration of water. Now, the next piece which comes out over here is this concentration of water we can calculate over here because it's a liquid. Liquids are going to be having a constant density and the water is going to be the solvent in this particular case here. What is the idea behind using it as a solvent? It is going to be in large excess. So if this guy is going to be in large excess, what is the next piece which we can basically go for here? So large excess is what this fellow is going to be present in. So we can then assume that density for this is going to be 1 gram per ml. So the density is going to be 1 gram per ml. That means 1 liter of water. If I am taking, I can now calculate the concentration of water associated with this as 1000 by 18, which of course works out as 55.57 or 55.56, 55.55 bar actually. You're familiar with this already, I suppose, yes?
Yes, sir.
Okay, all right. So when you're going to be having it like this, you're going to be having the K equilibrium now can be written again as H3O plus concentration into A minus divided by HA into H2O. So this guy is going to be a constant which is going to be approximately equal to 55.55. But even if it is not exactly equal to 55.55, even if it is slightly lesser because there is something else now dissolved in it, it is still going to be a constant more or less because it's going to be in much larger excess. So what do we do over here? We apply the chemical kinetics aspect of it. We combine it with that because K equilibrium is what? K forward by K backward. Rate constant of forward by rate constant of backward, meaning this is going to be nothing but rate constants only. So technically it's going to be chemical kinetics. I can apply theories of chemical kinetics and I can consider it as a pseudo type of order in that backward direction or whatever direction which you are going to be having. H2O is the products there. So or H2O involved over there. H2O can be considered as something which is going to be pseudo, whether it is reactant or product. It doesn't make a difference because it is approximately a constant. So we can now say K equilibrium into concentration of H2O is going to be equal to H3O plus into A minus divided by HA. This is going to be something which we now give a new name. We call it as Ka, which is also called as dissociation constant of the weak acid HA in water. The in water part is usually neglected. We do not bother mentioning it. Why? Because we assume it is going to be in water always. But in some cases, they can change it from water to some other system also. We'll talk about that in a bit. So Ka in water is generally going to be assumed over here. So it is called as dissociation constant for this weak acid HA. So when you're going to be looking at any random weak acid HA, we don't need to now think about writing every time as H3O plus, because if H plus is present in aqueous condition, that automatically means it is going to be present only as H3O plus. Free H plus does not exist in water. So when you're going to be having H plus, it is like an electron, it is a proton. No proton or electron exists freely for any amount of time which we can observe it for. Remember, only when we can observe it do we say we know it exists freely. Remember that clearly. So observation directly is when we say it exists freely. Means it exists freely. Till we can actually observe it properly for a decent amount of time, we cannot say it exists freely in that system. So yes, we can isolate a proton, we have isolated an electron, all of that we have technically observed it, all of that we have done. But not when it is existing freely for a decent amount of time, not in a particular system which we can continuously keep doing that. Okay, so H plus and electrons do not exist freely. Under normal conditions. We are doing chemistry, so yeah, I'll have to give the caveat that there is no 100% ever. There will always be something new discovered which will basically change the game there. So when you're going to be having this particular thing being taken as the standard equation for any random acid, then we can straight away define Ka for a random weak acid simply as H plus concentration into A minus concentration by HA. That is going to be the Ka for a weak acid. Of course, this includes in water. If you're doing it in another solvent, you will have that own solvent's constant applicable there, which will be different from the constant for water. So you have to then adjust for those constants as necessary mathematically. Okay, so next up, the same thing applies for a base over here also. A base, effectively, let's say I'm taking ammonia as the base. Ammonia is going to be a typical base. Let's say ammonia is reacting with water. Ammonia is a proper Bronsted-Lowry base, not just a Arrhenius base. It's not an Arrhenius base, it's only a Bronsted-Lowry base. So if this guy is going to be reacting over here, the ammonia will accept H plus from water here, resulting in becoming NH4 plus, and water ends up becoming OH minus in the process. So technically OH minus is produced, but it is produced by water being forced into kicking out that OH minus. So again, equilibrium constant, same way K equilibrium is going to be NH4 plus into OH minus divided by NH3 into water. Again, this water is going to be a constant. Because it is going to be a constant, we can effectively now write K equilibrium into water is going to be equal to NH4 plus into OH minus divided by NH3. So effectively we will end up having this K equilibrium into water now being looked at as what is called as Kb for any weak base. So we will now have a next equation over here, Kb for a weak base being something which we can write as, if it is going to be a general base, B giving BOH, something not exactly like what to say ammonia, but something which is more like Arrhenius. We will end up having it as B plus into OH minus divided by BOH. Oh damn, I should not have written as B. Made mistake there. BOH. Aqueous of course everywhere. We'll have it as B plus into OH minus divided by BOH over here, working out as what is going to be the Kb for the weak base. So now we are going to be having two separate expressions which are more easier to manipulate mathematically. Ka for a weak acid is going to be nothing but H plus into A minus divided by Ha. Whereas for the weak base we are going to be having Kb for the weak base being B plus into OH minus divided by the BOH, or the base which is there in question over here. Okay, so now let's go back to Ha. Let's understand this equilibrium a little bit more carefully mathematically over here. So let's say C is the initial starting concentration for my HA in solution. We'll have these two at 0, 0 at starting. When the equilibrium is not yet reached, it is starting. I've just thrown in some HA into my solution over there with water. I'm going to be having this happening. So we'll have Ka as the equilibrium constant here. Alpha is going to be as expected as a previous definition. With respect to 1 mole of what I say substance, we'll define alpha. So C into 1 minus alpha, C alpha, C alpha. We end up having Ka can now be written as H plus into A minus divided by Ha, which can of course be written as C alpha into C alpha divided by C into 1 minus alpha. C and C cancel out, so it works out as C alpha squared by 1 minus alpha. So this is going to be your expression when it comes to Ka for the weak acid now. Now this is where things get interesting here. Now equilibrium, especially ionic equilibrium chapter, is all about approximations, because ultimately we cannot really sit and calculate everything perfectly mathematically, because they are all technically going to be at a scale where the functions which you have to use to calculate them are much more complicated. So easiest way, approximate wherever possible in the most meaningful manner, but check once after you have done your approximation, once you have got an information piece done, check if that approximation is correct or not. In this particular case here, the approximation we are going to be using is, if Ka is less than 10 power minus 3, what we end up having is, we can generally say 1 minus alpha, or rather alpha in this particular case will be very much less than 1, which basically translates into the next approximation, which is that 1 minus alpha can then be approximated as equal to 1. That is the approximation which we are going to be looking for and which we'll be using over here in this particular case here. So we will have this one now after the approximation is dealt in. What does this become? This becomes Ka for the weak acid is going to be equal to approximately C alpha squared, which means from this case we will now be having alpha being approximately equal to square root of Ka divided by C. Now in this particular case, concentration of H plus was C alpha over here. So if concentration of H plus is C alpha, that means we can write concentration of H plus is going to be C into this alpha which we have calculated here. So it works out as square root of Ka into C. This is going to be the next expression here. Lastly, we are going to be having, if concentration of H plus is this, we can of course now define pH over here as half into pKa minus log C. Now what is this pK nonsense which I am defining over here? It is the same definition as pH over there. P of x is going to be nothing but minus log of x. That is how we define that p function over there. So obviously P of Ka becomes minus log of Ka. So it is half into minus log Ka minus log C, which is what we are getting over there. Effectively minus log of H plus is pH. So minus log of square root of Ka into C. Square root is power half, so half comes out. So these are three equations which are going to be very important, which are very much necessary for you to basically memorize. and you need to remember the case at which this is going to be applicable. Okay, now let's proceed on to the next part over here. When it comes to a weak base, all right, the same type of expression happens over here. B plus plus OH minus, all are aqueous. So starting is C, 0, 0 at equilibrium. This C alpha, this thing is at equilibrium, by the way. So yeah, sorry, I should have mentioned that earlier. So at equilibrium, what are we going to be having over here? We are going to be having C into 1 minus alpha, C alpha, C alpha. Excepting in this case, mathematically, we are calling it as KB. So everything looks the same, everything is the same. So we end up having KB equal to C alpha into C alpha divided by C into 1 minus alpha. Same mathematics applies. So again, in this case also, if we are going to be having, if KB is less than 10 power minus 3, we can use approximations. What approximation? 1 minus alpha is approximately equal to 1. So you're going to be having the same type of equations now being applicable for KB also. So let me put them down properly in one spot over here. So for weak acid, the equations which you need to memorize are the following over here. If Ka is less than 10 power minus 3, you can use these approximate equations. If Ka is not less than 10 power minus 3 or it is more than 10 power minus 3, no escape, sit and solve the quadratic. I'll show the quadratic, what has to be solved in the next page over here quickly. So the quadratic which needs to be solved in that particular case will be Ka is equal to C alpha squared by 1 minus alpha. So this is the quadratic to solve. To solve, if Ka is greater than 10 power minus 3. Equal to 10 power minus 3, you will be getting, you can use both, no problem, it's a boundary case. Effectively, the approximation is going to be barely acceptable. That is what I mean by Ka equal to 10 power minus 3 case there. Of course, once you have solved, what do you solve for? Solve for alpha first. Or whatever is your unknown in that particular case. Once you have solved for alpha, then C alpha is equal to concentration of H plus. From there, calculate pH. That is basically the methodology if you're going to be having Ka being greater than 10 power minus 3, or simultaneously, of course, is also applicable for Kb greater than 10 power minus 3 also. In that case also same thing, excepting once you solve for alpha, you'll be going for C alpha, which is now going to be equal to concentration of OH minus, and from there you'll go for POH instead, not pH. That is going to be the difference when it comes to the weak base case over there. Alright, so now let's look at the equations which you need to memorize over here. These are equations you have to memorize. Why do I say memorize? I don't like memorizing realistically. I don't like asking people to memorize, but memorization is a tool. A very, very useful tool which will help you in solving questions faster. I'm sure you have already recognized it, so I'm not going to go into the importance of memorization. So usefulness of memorization is what I should say there. So when you're going to be having a weak acid, if Ka is going to be less than 10 power minus 3, what are the equations which apply there? You're going to be having alpha being equal to square root of Ka by C. You have H plus concentration is equal to square root of Ka into C. And lastly, pH is equal to half into pKa minus log C. All these three are applicable if Ka is less than 10 power minus 3 for any system which technically, mathematically can be defined as a weak acid. Alright, that is the idea over here. Now, the same thing we can now obviously convert, because weak base ke liye same equations mathematically are applicable, excepting small adjustments are needed. So in this case here, for weak base, if I am going to be putting down the equation becomes, if Kb is less than 10 power minus 3, how do you convert? Alpha is going to be Ka becomes Kb. The conversions are these. Ka changes to become Kb. Concentration of weak acid becomes concentration of weak base. Both are represented by C, so we don't care. Obviously, pKa will become pKb. And we'll of course have pH becoming pOH. And concentration of H plus will become concentration of OH minus, wherever it is applicable. One more thing which will actually change is conjugate acid will also change into conjugate base. And wherever it is weak base, it will become weak acid. Wherever it is weak acid, it will become weak base. Let me rub off this line partially now. Last one is, we end up having weak acid changing into weak base. Any concentration of weak acid. So alpha in this case works out as square root of Kb by C. concentration of OH minus works out as square root of Kb into C, and POH works out as half into pKb minus log C. These are the three equations here. Remember one of these sets, convert the other. Do not sit and try to remember the other. It is a waste of time. It is not worth remembering. Don't store unnecessary junk in your brain. Remember how to do the conversion internally so that you need to waste time on that, and directly start off with the original equation itself as it is. So remember for weak acid ideally, or for weak base, I don't care. One of them, remember all three of these equations. Now next up, we are going to be having okay, weak acid, weak base are effectively done. The simplest part of it is done. Now we can shift into water. Now when it comes to water, we had discussed that water is going to be something which can behave as both an acid and a base. Why? Because water can create its own equilibrium where it can technically produce a H plus and an OH minus. But we have already learned there is no H plus. So technically this equation is not perfectly correct. If I have to study more carefully, I should technically study H2O plus H2O in equilibrium with each other. One of them behaves as an acid, the other fellow behaves as a base. So one of them donates H plus, which is accepted by the other to become a H3O plus, and the one which donated the H plus and behaved as an acid will now end up becoming an OH minus. This is going to be having an equilibrium constant also. This K equilibrium here we can now calculate and study. So when scientists did this, they effectively had the equilibrium working out like this. It was actually H plus into OH minus divided by H2O into H2O. Now they realized that water is something which is behaving something like a weak acid and as a weak base. So if this guy is behaving as both weak acid and weak base, technically having some way to compare it with what is going to be a normal weak acid and a weak base is mathematically very useful always. So the next stage of this was to mathematically compare it with a weak acid or a weak base, which is normally going to be in water. For which, how do we compare? We use mathematics to compare. We have derived a new dissociation constant Ka and Kb, which are both in water. So we use that analysis to compare over here. So how do we now write this? We write this slightly differently. K equilibrium into concentration of water, because concentration of water is completely a constant. So when it is going to be a constant, we can now combine it with the K equilibrium there and compare it. But this is not the comparison we are going to be doing actually. This is going to be something which is now comparable to Ka or Kb. But in reality, what is changing for water? Let's now study that equilibrium a little bit more closely. So K equilibrium here is H plus into OH minus divided by H2O squared. Correct. H2O is going to be a constant actually. Yes, the H plus and OH minus are also not going to be changing much. They are also going to be a constant at equilibrium, but they are very tiny when compared to water. Constant high. So we can now combine it with the equilibrium constant. So that's what they did. So scientists could experimentally calculate K equilibrium into H2O squared much more easily. So they did that. And that was something they calculated as what they newly called as dissociation constant of water, which worked out as 10 to the power of minus 14. And this was equal to concentration of H plus into OH minus in any solution of, in any system where you are going to be having solvent as water. And just like all equilibriums, it is going to be something which is a rate constant expression, effectively speaking. When I say rate constant, some forward, some backward expression is going to be there. Which forward, which backward? This forward, this backward. Alright, it involves this forward, this backward. So you're going to be having, that is going to be effectively something which is going to be a rate constant, meaning it depends on temperature. So this is at 25 degrees Celsius or 298 Kelvin. So this was calculated out for that particular condition specifically. Okay, now this Kw over here is going to be simply called dissociation constant of water. But this doesn't give us the correct way to compare it with other Ka and Kb values. The more efficient way to compare it with actually the Ka and Kb values is K equilibrium into H2O is comparable to Ka or Kb. Comparable, now it is similar to them mathematically speaking. So if I have to make a comparison and understand how strong, what is the Ka value for water or Kb value for water, I need to do this comparison. This is of course going to be nothing but Kw was K equilibrium into H2O squared. So it's Kw by concentration of water. So if it's Kw by concentration of water, we can say Ka or Kb for water like weak acid or weak base in a manner similar to that is going to be 10 power minus 14 divided by concentration of water. Concentration of water is of course going to be 1000 by 18. So we'll be having it as 10 power minus 14 divided by 1000 multiplied by 18. Sorry, 1000 divided by 18. Sorry, 1000 divided by 18. So 18 will go to the numerator here. So it works out as 18 into 10 power minus 17, which works out as 1.8 into 10 power minus 16. So we can say Ka or Kb, when you are going to be comparing for water as a weak acid or a weak base, both are going to be the same because it produces both H plus and OH minus at the same time. That is going to be 10 power minus 16 into 1.8 like this. This is basically the value which you are going to be having for Ka or Kb comparison. So when you want to compare, say, which will behave as a base in water or which will behave as an acid in water, how do you decide? So the way to decide goes like this. If Ka for a weak acid is great, okay, I should not put it like this, I'll put it mathematically, that will be easier. If Ka for a weak acid is greater than Ka of water, implies this guy behaves as acid with water or behaves as weak acid in water. If it is not, it cannot behave as a weak acid. As simple as that. For instance, in organic chemistry, you have learnt about how acetylene is going to be something which is going to be having an acidic hydrogen, correct? You are familiar with this? Yes, you remember this properly?
Yes, sir.
Okay, cool. All right. So this is going to be an acidic hydrogen now. This hydrogen is going to be something which will also have a Ka. So there will be a Ka associated for acetylene over here. But this Ka is actually going to be lesser than the Ka for water. What does this mean? This means this does not react as an acid in water. Implies acetylene does not react as acid in water. That is a simple idea over here. But it does react as an acid with something like a Grignard reagent, because Grignard reagent is a much more powerful base. So with that guy, this fellow will react as a base over there. This fellow will react as an acid over there. So you are going to be having this being very low. In fact, it is lower than OH minus also. That is why OH minus also does not react with this guy here. Sodium hydroxide does not react as a base, correct? What does that mean? That means even sodium hydroxide's basic character, OH minus's basic character in water is not enough for this. So it is going to be a weaker acid compared to even oxide ion. Alright, so it is not just a weaker acid than this, it is a weaker acid than OH minus also. Anyway, no, sorry, it is not a weaker acid than OH minus, but yeah, it is a weaker acid than water. Because it's a weaker acid than water, does not react with OH minus. The organic chemistry interpretation is does not react with OH minus. That is the basic idea over here. Or you can say it does not dissociate into water as a weak acid over there. Okay, so now this is the Ka or Kb understanding or interpretation for water. And for water, you are going to be always having this Kw being equal to 10 power minus 14 equal to H plus into OH minus at 25 degrees Celsius or 298 Kelvin. So all ionic equilibrium expressions which you are studying in Bronsted and Lowry, all mathematics you do, we are going to be using this as the basis there. We are going to assume it is going to be at 298 Kelvin. Okay. Next up, we need to discuss one other piece of information over here, which is going to be what is called as hydration and what is known as hydrolysis. So let's talk about hydration over here. Hydration means ion or system, whatever that system is going to be, I don't care really, is very stable in solution with water. What does this basically lead to? It does not react at all. What does this does not react at all basically indicate? It indicates it does not affect pH of solution. And we generally call these kind of ions as spectator ions. Basically, they are like spectators in a match or in a game. So they are not going to be participating. Yes, they can influence, but they can't participate directly. So now in this particular case here, this hydration is going to be something where we can now understand what is happening a bit more clearly. So what happens in this particular case here, these ions are going to be simply surrounded by water molecules. So if I'm having an Na plus, the O delta minus part of it, O delta minus part of water will completely surround the Na plus totally. When it surrounds the Na plus totally, what is going to be happening? The Na plus ion will be having, ion dipole attraction with the water molecules right now. So when the Na plus ion ends up having ion dipole attractions with the water molecule, you'll have Kq1 Q2 by R squared and Kq1 Q2 by R playing a role, which will effectively stabilize the Na plus ion in solution properly right now. Same thing happens for my Cl minus ions. So in this case here, you're going to be having hydrogen part of water basically surrounding it. So same thing will basically be surrounding this flow also. So when you're going to be having these kind of ions over here, Na plus or Cl minus, one interesting piece to notice about them is they are going to be effectively going to be nothing but Na plus over here is technically going to be conjugate acid of a strong base. What is a strong base here? NaOH. Strong base in water. So if something is capable of behaving up to 100% extent, 0 is going to be the boundary which it tends to, a defined boundary. Then you're going to be having in this particular case here, 0 amount of it is left over. That's what I mean. So in this particular case here, conjugate acid of a strong base in water like NaOH is going to be something which will undergo this kind of a hydration over here. Another species which does the same thing is of course going to be the conjugate base of a strong acid in water. Like in this particular case, HCl. So that is also going to be producing what is going to be a spectator ion in this particular case over here. Next up is hydrolysis. What is meant by hydrolysis over here? Hydrolysis basically is obviously giving you, the name itself is telling you roughly what is happening. Hydro mein lysis is happening. Electrolysis means using electricity or in the presence of electricity, some bond breaking is happening. So any lysis means in the presence of that bond breaking is happening. Hydrolysis means some bond breaking happens. In water. It can be that original fellow is breaking, or it can be that it is breaking water. Both are acceptable as hydrolysis. So some bond breaking happens in water. You can say original compound breaks. The breaking can be partially or fully. If it is fully, it automatically goes into hydration case that they'll stabilize. So some bond breaking happens, and a more exact definition would be partially, not fully. So it can be either original compound breaks or original compound helps water break. These are the two ways we can understand what is basically going to be happening in hydrolysis. One critical feature about hydrolysis though is this. Since bond breaking happens, so what happens when bond breaking is happening? You're going to be having an electrophile nucleophile type of pair being created. One thing which is more electron rich, another which is less electron rich. So you're going to be having some kind of increased polarity. Effectively, increased polarity is going to be there. No need to call it increased polarity, that is not the perfect term here. So some kind of change in pH is going to be happening there. I'm just going to give you the mathematical idea there. Since bond breaking is happening, technically you are going to be, the idea there is increased polarity is there. Because increased polarity is there, more of water molecules end up breaking, or more of the dissociation of water is visible. So since some bond breaking is going to be happening, some kind of an acidic behavior or some kind of a basic behavior increases over there, which results in pH does get affected. By hydrolysis. So when you're going to be having hydrolysis happening, your pH of the solution does get affected and it will end up changing. How much by? That depends on what is doing the hydrolysis or what is undergoing the breaking over there. If it is something which is coming under the hydration category, it may change the pH abruptly and then stop changing. If it is something which comes under the category of not breaking completely, it will not change the pH abruptly, it will change it slowly. Again, it will come to a constant. If it breaks completely, it is not necessarily hydration, it is ionic type of breaking, and parts of it might end up being spectator, parts of it will change pH abruptly. All of that can happen. So we'll be studying all of that in more detail in the coming parts over here. So let's now understand different types of salts and learn a little bit more about them. So before we go into the salts, let's study the conjugate acid and conjugate base of different systems. So first off, conjugate base of a weak acid we are going to be studying. When I say weak acid over here, we are going to be considering weak acid meaning stronger than water. What does that mean? That means it is capable of behaving as a weak acid in water. And the extra thing is you are also going to be having Ka value being less than 10 power minus 3. Why? So that we can use our approximations, no other reason. So we'll be studying conjugate base of a weak acid, and of course we'll be studying its counterpart, which is going to be conjugate acid of a weak base. Again, same conditionalities, stronger than water as base. Stronger than water is enough. And of course, Kb should be less than 10 power minus 3, not greater than. If it's greater than, we'll have to sit and solve unnecessary quadratics, not worth it. So we are going to be looking at all the approximations, how the mathematics effectively translates into a larger piece. Alright. So let us now try to understand one of these things. Mathematics automatically will translate, so we don't need to study both of them. So let us now study A minus, which is going to be HA's conjugate base here. So if I consider HA here, it breaks into H plus plus A minus. So this is my weak acid. So this guy becomes conjugate base of weak acid. So we are now trying to study A minus in this particular case here. So if I am trying to study A minus, it is a conjugate base, meaning it has to behave like a base. So let's try to study how its behavior as a base looks like, and then think if its mathematics is making sense or not. So if A minus is going to be behaving as a base with water, we'll end up having the equation as A minus behaves as a base. So if this behaves as a base, so if the A minus ends up behaving as a base, it accepts a H plus. So it accepts a H plus means it becomes HA, and the water is the one which should have behaved as the acid here and donated the H plus, meaning the water becomes an OH minus in the process over here. So A minus and HA are going to be now systematically present in the equilibrium here. So let's now try to understand what is going to be happening over here. We will have this as Kb for my A minus. That is the idea over here. So let's study this Kb for A minus a little bit more carefully. So Kb for A minus can be written as HA into OH minus divided by A minus into H2O. So I'll have it as HA into OH minus divided by A minus into H2O. This is going to be the case. So, but if I am writing it as Kb over here, what is the idea here? That means H2O is included as part of the K equilibrium. So technically I should not put a water here. It should only be without the water, because if I am writing it as Kb, automatically I am including the H2O concentration there. So we can effectively write Kb of A minus being HA into OH minus divided by A minus concentration. Now all things are at equilibrium here. That's what we are trying to study. That means H plus concentration is also a constant. So I can now multiply and divide by concentration of H plus. If I do that, what is going to be happening here? I am going to combine these three pieces now, and I am going to be combining these two pieces now. So what do we end up having? These two pieces, the blue part over here can be combined and written as Kw, whereas the pink part over here can be combined and written as divided by Ka. Because H plus into A minus, the HA, if I am bringing it to the denominator, it becomes 1 divided by Ka, so effectively it becomes Kw by Ka. Meaning we can now write Kb of my conjugate base of a weak acid is going to be something which, if I am going to be writing it, it is going to be Kw divided by Ka for the parent weak acid which we were considering. This is going to be the expression here. So now let us try to understand how this works out mathematically over here. If I am going to be considering this working out mathematically, the Ka for this is going to be something which is for a weak acid. For our mathematical expressions, what have we considered? We have considered if Ka is less than 10 power minus 3. That is the mathematical consideration we have done usually. Of course, now there is a different boundary condition which comes in because Kw is 10 power minus 14 over here. So Kb is usually going to be in the bound for the conjugate base. If I am going to be putting it, it will be 10 power minus 14 by something in the range of 10 power minus 3 or lower. So less than 10 power minus 3 is what we have. But technically, if it is less than 10 power minus 3, let's substitute 10 power minus 3 and see what we get over here. So I am substituting 10 power minus 3. What we end up having over here is, we will now have this working out as 10 to the power of minus 11. This is of course something which is again Kb of the conjugate base here is less than 10 power minus 3 over here. Meaning the expressions which we derived mathematically earlier are all applicable for this system. So let us now try to extrapolate the equations which we have now gotten first and then see how to mathematically start using them more meaningfully. So this equation mathematically can be extrapolated now as Kb of conjugate base of weak acid is equal to Kw by Ka of weak acid. Yes. So Ka for conjugate acid of weak base can be written as Kw divided by Kb of my weak base in this particular case here. I'll be pushing through a little bit more faster from here. Equations will start flowing a lot more. So if you are not following at a particular point, please bluntly stop me and ask. Okay? Fair?
Yes, sir.
Okay.
Yes.
So this is again going to be technically applicable if my Kb, mathematics of it will be applicable if Kb is less than 10 power minus 3 usually. Mathematics of it is applicable. The equation is applicable everywhere. Mathematics of it is applicable only when the Kb is less than 10 power minus 3 when you are going to be using the math associated with it. When I say math associated with it, every equation associated with it, which is going to be non-approximate, which is going to be approximated. So let us now try to study different types of salts and the hydrolysis associated with them, or whatever happens when a salt is present in water. So we have currently broken down salts into categories of, or the acids and bases into categories of strong and weak. So the salt categories here are also going to be very blunt and straightforward here. We'll have 4 types of salts: salt of strong acid, strong base; salt of strong acid, weak base; salt of weak acid, strong base; and lastly salt of weak acid, weak base. We are going to be studying all 4 of these in more detail now. So let's start off with salt of strong acid, strong base. So when I'm considering salt of strong acid, strong base, a typical example is NaCl, where I'm going to be having both fellows being strong over here. NaOH is also a strong base in water. HCl is also a strong acid in water. Again, all of these are in water. They are not to be defined outside of water, because all of these definitions, they all come based on water. So everything is defined based on water here. So it is all applicable only in water. So if I'm having NaCl taken over here, this will basically be an ionic salt. Ionic salt means it undergoes complete dissociation. So because it's going to be ionic, if it dissolves, of course. If it doesn't dissolve, it doesn't dissolve. So ionic salts which dissolve, we are going to be assuming break down completely, at least in the beginning. Then some equilibrium might happen if there is equilibrium worthwhile. So NaCl here breaks into Na plus Cl minus, aqueous, aqueous. Both of these buggers are going to be your spectator ions, meaning do not affect pH of solution. meaning my pH of a salt of strong acid, strong base will straight away be equal to only 7. It is going to be same as neutral pH of water. Okay, this is going to be the case when it's going to be a salt of strong acid, strong base. Now let's go for the next case here. If I'm going to be considering a strong acid, no need to take strong acid, weak base. Okay, chalo, strong acid, weak base salt. If I consider the salt of a strong acid and a weak base, this is going to be typically something like ammonium chloride. Alright, ammonium chloride here is also an ionic compound, meaning this also dissociates completely when it is present in water. What does it dissociate into? It dissociates into ammonium ions and chloride ions. These chloride ions are going to be again spectator ions. So it does not affect pH of water. That part of it is going to be applicable for this also. So no effect on pH. So we can ignore. So I can ignore this guy in solution completely. I don't need to care about it. The ammonium ion though is going to be the unique fellow here, which is going to be having some issues here. This guy is going to be conjugate acid of weak base. What weak base? Ammonia. Now ammonia, when I am going to be considering, what is the Kb value of ammonia approximately? Now the Kb value of ammonia approximately is going to be 1.8 into 10 power minus 5, which I am going to be approximating further as 2 into 10 power minus 5 for easier calculation wherever necessary. So Kb value of ammonia is approximately 2 into 10 power minus 5, meaning we have now gotten the Ka expression out over here. Ka for conjugate acid of weak base is going to be Kw by Kb of the weak base. So now let's pay attention to this over here. What do we end up having in this case here? So Kb of ammonia is known. Now I can now extract out Ka for conjugate acid, which works out as Kw by Kb of weak base, which is ammonia here. Meaning now I can write Ka for NH4 plus, which is my conjugate acid of ammonia, is going to be 10 power minus 14 divided by Kb of ammonia, which means this works out as 10 power minus 14 by approximately 2 into 10 power minus 5, which works out as 10 power minus 10. So it works out as approximately 5 into 10 power minus 10. So my Kb of ammonium ion, which is going to be nothing but the conjugate acid of weak base, is going to be 5 into 10 power minus 10. This is of course saying that the Kb in this case for my conjugate acid is less than 10 power minus 3. What the heck? Conjugate base of weak acid. Oh, damn it. Yeah, sorry. If I'm making these kind of silly blunders, do mention, dude. Conjugate base of weak acid. So my Kb for conjugate base of weak acid here is less than 10 power minus 3. So if it is less than 10 power minus Kb, mistake here. It is supposed to be Ka, not Kb at all. So the definition part there was correct, but I should not have written as Kb there. Damn it. Because it's weak base we are studying now. Okay, So I'm going to be having Ka for ammonium ion, conjugate acid of weak base, and Ka for conjugate acid of weak base over here. It is less than 10 power minus 3, meaning all approximation equations are valid, can be used. What do those equations give us over here? We are going to be having 3 equations applicable there. We have alpha being equal to, alpha here is effectively going to be nothing but extent of whatever hydrolysis which happens. What is the hydrolysis which will be happening here? Ammonium ion reacting with water. So when you are going to be having NH4 plus reacting with water, it will of course end up giving me H3O plus NH3. This will basically be having some Kb over here, some Ka over here. That is going to be the Ka for conjugate acid, which we have now calculated as 5 into 10 power minus 10 approximately. And there is going to be an alpha associated for this. This reaction is called as the hydrolysis reaction. Why is it called hydrolysis? There is some bond breaking happening, and that bond breaking is happening incompletely in the presence of water. That is why it is going to be called as hydrolysis reaction in this particular case here. So hydro means it is happening in water, lysis means some bond breaking is happening, or some bond breaking obviously will, when there is bond breaking, bond forming will also be happening simultaneously. So some bond breaking and possibly followed by some bond forming is also happening, some bond change is happening in water. Okay. Oh, 1 second. So when you're going to be having this as a scenario over here, this is going to be the bond analysis, bond breaking and forming which is happening in your water over here. So you got the Ka value done for it. So if Ka is going to be applicable over here, alpha is the extent of hydrolysis for this particular equation over here, because this is a hydrolysis equation. So this can be called alpha of hydrolysis equation. So sometimes this is also going to be mentioned as alpha for the hydrolysis of salt of, in this case, weak base and strong acid. Okay, so this alpha here is the extent of hydrolysis here. We can calculate this as square root of Kb by C. Next up, we will of course be having concentration of OH minus, because it is going to be nothing but, not OH minus, damn it, yeah, concentration of H plus, because it's going to be nothing but conjugate acid of weak base. So conjugate acid of weak base, now we are going to be having, again this is not Kb here, I made the mistake here again, this is Ka by C. Damn it. Okay, so the H plus concentration here in this particular case works out simply as, we are going to be having square root of Ka into C. Same weak acid equation is applicable, square root of Ka into C. And lastly, the last equation, which is also going to be the extension of this, pH is going to be equal to half into pKa minus log C. So we can apply all three of these equations here. Let's now directly look into how these equations work out over here. So this Ka of conjugate acid, the expression we got was Kw by Kb of weak base. So when you're going to be writing it over here, we'll end up having alpha being equal to square root of Ka by C, and we'll have H plus concentration being equal to square root of Ka into C. That Ka is going to be nothing but Kw by Kb. So pH, if I'm going to be calculating, that is minus log of H plus concentration. So it works out as half into P of Ka minus log C. In this case, what is C? C is going to be concentration of NH4 plus ion, which is my concentration of conjugate acid. Okay, so P of K. Ka here is Kw by Kb. So let's substitute this fellow over here directly. So this works out as half into P of Kw by Kb minus log C. This is of course a logarithmic function. So log P is a logarithmic function. So log of A by B is log A minus log B. So this automatically works out as half into pKw minus pKb minus log C. So this is going to be pH of solution containing NH4 plus ion, which is going to be the only thing which is going to be critical here. But of course, you are also having Cl minus. Cl minus is just spectator. So if the solution is only containing NH4 plus, it has to have a conjugate anyway, it has to have the partner anyway. That partner in this case is Cl minus. Cl minus behaves like a spectator. NH4 plus is the only thing which affects the pH of the solution. Water, of course, is already included over here. That's where your Kw part comes in. So this equation, pH of NH4 plus, is also the same as pH of NH4Cl, which can also be considered the same as pH of salt of weak base and strong acid. In the sense, this is going to be conjugate acid of weak base. So effectively, you're going to be having it as salt of weak base and strong acid over here, which can effectively be written as half into pKa minus log C. What is Ka though? Ka for the conjugate acid has to be used over here. That is going to be Kw by Kb of my weak base. Now, of course, in this case, ideally this equation should be applicable now. One critical thing is the Ka for the conjugate acid should be less than 10 power minus 3. That is the necessary condition for this to be used over here. If it is not less than 10 power minus 3, you can't use this. So if I have Kb for the weak base being 10 power minus 17, what will happen then? If Kb for weak base is equal to 10 power minus 17, weak base equations apply for the weak base. But I can't use this salt hydrolysis equation over there. Why? Because if Kb for the weak base is going to be 10 power minus 17, that means Ka for the conjugate acid will be equal to 10 power minus 1. You understand the principle to be followed over here? Or you are following it to some extent? So this equation falls apart. I should not use this equation over there. I am capable of using the conjugate acid. This part equation is perfectly correct because this equation is always applicable. This is purely just equilibrium equation. There is no approximation there. But approximation is there when you are going to be having this equation applicable over there. That is, this equation has an approximation. So how does this equation translate into? You don't need to memorize any extra equation for this. Just translate it straight away. We end up having this is equal to half into P of K is P of Kw by Kb. So it works out as Pkw minus Pkb minus log C. You are clear with this properly now? Any doubts in this? Okay, alright. So next up, same type of logic. Now we can apply again for the other fellow also, which is the salt of weak base. Sorry, I just did that. Weak acid and strong base now. So weak acid and strong base now, my salt we are going to be considering is CH3CO minus Na plus. CH3CO minus Na plus, I am going to write it as Na plus A minus. Easier. I don't want to write too much. That's all. So Na plus A minus over here is a salt I am going to be considering over here. So in this particular case, this fellow will dissociate completely as Na plus plus A minus. Na plus is going to be my spectator here. So if I have starting concentration of this salt as C, these two would have been 0 and 0 at the starting. Then what will happen? Because an ionic salt, this will dissociate completely. This will become 0. This will become C. This will become C. But this is a spectator. So I don't need to care about this guy. This guy I don't care. Ignore. Why do I ignore this? Does not affect pH. Or pOH. pH affecting means pOH also gets affected because H plus and OH minus are in equilibrium with that Kw part there. So we are going to be having A minus being the only main thing over here which undergoes hydrolysis. So A minus undergoes hydrolysis. How is the A minus's hydrolysis going to be happening? A minus behaves like a base in water. So it will end up behaving as a base in water. What is it going to be doing? It is going to be accepting a H plus from water because it behaves like a base, and the water acts as an acid to produce an OH minus. So in this case, A minus is not breaking, but A minus is making H2O break, but A minus is forming a bond. So it is involved in the bond change or the bond exchange over here. So think of it as anything which is going to be capable of involving itself in a bond exchange in water, we can think of it as hydrolysis. So bond exchange in water is a more clinical definition which we can use over here when it comes to hydrolysis. Because of bond exchange in water, it affects the pH or pOH. Okay, so in this particular case here, we are going to be having this expression here. The hydrolysis constant is nothing but the A minus behaving as a base, so Kb of conjugate base of weak acid. Of course, you are going to be having all standard equations now being applicable. Kb of conjugate base is Kw by Ka for my weak acid. And if this Kb of conjugate base of weak acid, if Kb of conjugate base is less than 10 power minus 3, all the expressions we derived earlier are applicable. So now we will end up having, if Kb of conjugate base is less than 10 power minus 3, what are the expressions which get applicable now? we'll end up having alpha for hydrolysis is going to be equal to square root of Kb into C. Damn it, not square root of Kb into C, square root of Kb by C. Kb by C. Next up, we'll end up having concentration of OH minus being equal to square root of Kb into C. And lastly, of course, the main equation, POH of the solution. What is this? This is nothing but POH for conjugate base of weak acid, which can effectively be written as POH of salt of weak acid and strong base. All three of these can now be written as half into pKb minus log C. What is this going to work out as? It works out as Kb is Kw by Ka. So I'll just put that down over here. So Kb for the conjugate base is going to be Kw by Ka of the weak acid. Meaning we'll now be having this as simply half into pKw minus pKa minus log C. So again, no need to memorize this expression. Remember the conversions of how to do. Remember that this is going to be nothing but conjugate base of weak acid, meaning if the Kb for the conjugate base is less than 10 power minus 3, we can again use all the equations which we derived for the weak base where the Kb is going to be less than 10 power minus 3. Okay. Now I mentioned that you're going to be having, if the Kb of the weak base is 10 power minus 17, Ka becomes 10 power minus 1. This is the kind of boundary where your strong and weak basically end up interchanging. So you have to be careful on these boundary conditions. You have to pay attention to them and you have to watch out for them. Watch out for them. Now you can't use equations. You can't use the final approximations there. So these are basically hydrolysis of three different types of salts we have covered off now. So which ones are done? Strong acid, strong base is done. Next up, we are also done with salt of weak acid, strong base just now. And just before this, we were done with salt of strong acid, weak base. The last one which is left over is going to be weak acid, weak base. So let us now try to study salt of weak acid, weak base a little bit more carefully. So this is going to be something where you're going to be having two things available. Let's take a simple example of a weak acid, weak base salt here, ammonium acetate. You have more time available or you will be getting busy? What's your situation like? Another 15 minutes is okay?
Yes, sir. 15 minutes is fine.
Okay, I will shut up in 15 minutes. Okay, so if I'm going to be considering salt of a weak acid, weak base over here, let's say I'm taking NH4 plus CH3CO minus. This is my ammonium acetate. Let's say this is going to be having concentration as C in my initial starting. This is also going to be an ionic salt technically, alright, because it's made up of ions officially. So this ionic salt here technically should break down completely. So if it breaks down completely, it will produce NH4 plus ions and CH3CO minus ions. Originally 0 and 0, this will become 0 eventually, this will become C and C. Now issue here is, this guy is going to be conjugate acid of weak base and this fellow is going to be conjugate base of weak acid. So let us now try to understand their Ka and Kb values. So the general lucky thing which we are going to be using over here is Ka for CH3COOH is approximately equal to Kb for ammonia, which are both approximately equal to 2 into 10 power minus 5. They are not exactly this, they are approximately this, and they are close enough by that we can use this approximation comfortably, at least from mathematical perspectives. This straight away gives us one more piece of information over here. We are going to be now having Ka for conjugate acid, which is going to be ammonium ion, is approximately going to be equal to Kb of conjugate base, which is going to be CH3COO minus, which in turn are approximately going to be equal to 5 into 10 power minus 10. So both of these Ka and Kb values are 5 into 10 power minus 10 approximately. What can I now start looking at as conclusions over here? I can now say Ka for my conjugate acid, which is going to be Ka for ammonium ion, is greater than Ka of water. Correct? Because it's 5 into 10 power minus 10. Ka for water, Ka or Kb for water. What did we get that as? We got that value as 1.8 into 10 power minus 16. You remember that value? We just did that in one of the previous derivations today. So it worked out as 1.8 into 10 power minus 16 over there. So if I'm going to be now connecting these two over here, so my Ka of NH4 plus is going to be greater than Ka of water. At the same time, my Kb of CH3COO minus is also greater than Kb of water. What do these two particular pieces of information inform us? This tells us that this is stronger than water as acid. And the other one is going to be the stronger base. So what does this basically give us as the final piece of information over here? So when you're going to be having the ions in solution now, let's try to understand what is present in solution right now. So we are going to be having CH3COO minus, NH4 plus and water. All three of these guys are present. They are interested in reacting. Something has to react over here. Only problem is water is both the weaker or the weakest acid and weakest base in solution. Hence, does not take part in hydrolysis. So it is not going to be taking part directly in any hydrolysis over here. So if this guy is not going to be taking part directly in any hydrolysis, what is the advantage which we now end up having? The advantage which we now end up having is very simple. We now have only a direct equation between CH3CO minus and NH4 plus. So CH3CO minus will now react with the NH4 plus, and we will now have this as the new hydrolysis equation. And we are going to be having CH3CO minus being the conjugate base, and this is going to be the conjugate acid. Conjugate base of weak acid, this conjugate acid of weak base. So the CH3CO minus behaves as the base over here, meaning it will accept a H plus to become CH3COOH, and the ammonia ends up NH4 plus ammonium ion behaves as the acid to form ammonia over here. So if I start off with concentration C and C, and these two guys being 0 and 0, after the equilibrium has been reached, we will now have C into 1 minus alpha, C into 1 minus alpha, C alpha and C alpha. So we can now write this KH expression is going to be C alpha into C alpha products by reactants into C squared into 1 minus alpha whole squared. So the C squared and the C and C will cancel off. This works out as alpha by 1 minus alpha whole squared. Alright, so now let's try to understand the KH expression from some other point of view now. The KH here theoretically is going to be nothing but products present over here divided by reactants present over here. So products are CH3COH ammonia, reactants are CH3CO minus NH4 plus. Substituting them out, we end up having KH working out as CH3COOH into NH3. I'll write them out nice and separately so that it is easier to basically break it down next part, into NH3 divided by, we are going to be having CH3CO minus and NH4 plus. So we'll have CH3CO minus, let me put it here, NH4 plus, let me put it here. What I'm going to be doing now is I'm going to multiply and divide by H plus into OH minus, but I'm going to place them out carefully. So I'm going to be having H plus into OH minus, both sides, numerator and denominator, I'm going to be dumping them, and I'm going to now try to see how to manipulate the equation. These three I will now combine, and next up I'll be combining these three over here. And lastly, we'll be combining these two over here. This effectively results in the KH expression now being the white part on combination becomes 1 divided by Ka of weak acid, and the blue part automatically becomes 1 divided by Kb of weak base, and lastly the numerator ends up becoming Kw. So I can now effectively write this off as Kw by Ka of weak acid into Kb of weak base. This is going to be my KH of the expression over here, or the hydrolysis constant for the equilibrium which we are considering, which we have also calculated as alpha by 1 minus alpha whole square. Right, so you calculated this, guys, alpha by 1 minus alpha whole square. What else do we know from the expression over here? We can now connect with certain other equilibriums also. We also know that CH3COO minus is in an equilibrium with OH minus, in the sense this will be in an equilibrium with water. What is the equilibrium for this guy with water? This will be CH3COO minus plus H2O, or instead of writing it as CH3COO minus, we can write as CH3COH also, because all equilibriums have to be maintained. That is the idea here. So we can write a CH3COH equilibrium. That is easier actually. CH3COH should be in equilibrium with CH3COO minus and H plus. This equilibrium constant is supposed to be Ka. CH3COOH concentration here, that is going to be C alpha, whereas CH3CO minus is my C into 1 minus alpha. So substituting them over here, we end up having this is going to be C alpha, this is going to be C into 1 minus alpha. We don't know K, we don't know H plus over here, but we know this expression for K. K is H plus into C into 1 minus alpha products divided by reactants C alpha. C and C cancel off. So we end up having it as H plus into 1 minus alpha by alpha is going to be equal to Ka for my weak acid. Meaning we can write H plus concentration is going to be equal to Ka multiplied by alpha by 1 minus alpha. Now alpha by 1 minus alpha whole squared we got in the previous page over there as Kh. So this basically translates as alpha by 1 minus alpha is equal to square root of Kh, which can of course be written as square root of Kw by Ka into Kb. If I substitute this one into the next page over there, we will now be having the following over here. H plus concentration works out as Ka into square root of Kw by Ka into Kb, wherein we'll have the Ka going inside, so it works out as H plus concentration is equal to Kw Ka by Kb, entire thing inside a square root. Automatically the same kind of thing can be done for OH minus also. How will that work out? It is ammonium ion which is now in equilibrium. So NH3 plus H2O will have an equilibrium Kb, which is going to be NH4 plus OH minus. This is going to be C into 1 this is going to be C alpha over here, because NH4 plus is C alpha here and NH3 is C into 1 minus alpha. And of course you can sit and calculate it off over here in the same way over here. Oh no, I think I made the mistake here, sorry, it is ulta over here. This is C into 1 minus alpha, this is C alpha, sorry, mistake. So you're going to be having this as Kb. H2O you can anyway neglect here because it's written as Kb. So you can automatically get your OH minus here using this expression. Or you can also do the reverse calculation or the conversion part which we had discussed earlier, wherein you are going to be having OH minus concentration working out as square root of Kw into Kb by Ka. You can effectively put it like that also. So that also works over here. Now what does this finally lead to over here for this salt over here? So we can say pH of salt of weak acid weak base can be written as minus log of H plus, which in turn is going to be minus log of square root of Kw Ka by Kb. Meaning if it is already like this, we can directly now write it as half into pKw plus pKa minus pKb. This is the pH of the salt of weak acid, weak base. But it is not pH of any kind of salt. It is pH of something where you are going to be having equal concentrations, where it is something like NH4 plus CH3COO minus. Meaning, if you are not having equal concentrations, this will not work. So, both of these should effectively give out same concentration. So, if you are going to be having something like a slightly different salt, for instance, if I am considering say ammonium oxalate will become NH4 twice C2O4. This equation does not apply. Do you follow for why it doesn't work for ammonium oxalate? Because in ammonium oxalate, this will become 2C, this will become C. You understand the problem here? So you will not have the entire things getting cancelled out perfectly. You will have complications appearing over there. And when you are having complications appearing, equation which you have derived will not be applicable there straight away. Now, this equation is a very powerful equation. This is the next equation which you have to memorize here. So, let me explain why. Let me explain what is the idea over here. So, NH4 plus CH3COO minus C and C. In this case, this guy is conjugate acid. We can say this conjugate acid is similar to weak acid. And this guy is going to be conjugate base, which is going to be similar to weak base. And the key point here is concentrations are both equal. Weak acid type and weak base type are equal. If this is the case, for this kind of a case, we have now derived the expression that the pH is going to be half into pKw plus pKa minus pKb. This expression is very useful and very, very important because this expression is holding good for all cases like this. Now, what do I mean by this holds good for all similar cases over here? If I am given a solution of say CH3COOH concentration C and ammonia concentration C, pH, it doesn't matter if it is randomly mixed weak acid and weak base, pH is going to be half into pKw plus pKa minus pKb. Directly we can apply this and proceed on, no problem. This will give you the correct answer. Same way, if I am going to be having say some kind of a polybasic acid, if I have say H2A, H2A is a polybasic acid. So instead of having H2A, I will take the standard polybasic acid which everybody should be familiar with. You should definitely be familiar with this. This is there in organic also. So H2CO3 is going to be something which will dissociate as H plus HCO3 minus. Let's call this dissociation constant as Ka1. But this HCO3 minus is something which can still dissociate. When it dissociates further into the next level of acid and gives out one more H plus, it will form CO32 minus. This I am going to be calling it as Ka2. Now if I am considering this HCO3 minus here, in the first place here, this is going to be technically conjugate base of Ka1. But it is also going to be having weak acid as Ka2. So what is the idea here? HCO3 minus, the middle salt over here, is something which can act as a weak acid, in which case it is going to be Ka2, which is going to be this part here. But the same HCO3 minus is also going to be conjugate base of Ka1. Meaning, if I am considering the Kb for this, that is also something which we can now get. Kb for conjugate base of Ka1 is going to be the same as Kb for my HCO3 minus. This is of course going to be Kw by Ka1. What does this mean theoretically from, this is the mathematical theoretical understanding, what does it mean theoretically from an imagination perspective? Let's look at the structure of HCO3 minus. HCO3 minus structure will look like this. One ending is going to be an O minus ending. This is going to be the conjugate base of Ka1. And this ending is going to be weak acid Ka2. So, this white colored ending, the conjugate base of Ka1 ending, will be having Kb being equal to Kw by Ka1. Meaning, technically speaking, if I have any solution of HCO3 minus, or any middle salt is taken, for all middle salts this will work over here. We will be basically looking at those a little later. So if I am taking any solution of HCO3 minus over here, we will be having that solution of HCO3 minus. Same thing acts as same item, same HCO3 minus can act as both the weak acid, in which case it is going to be the Ka2 part over here, and weak base, which is going to be this Kb part over here, which is going to be conjugate base of Ka1 part. So it can act as both the weak acid and weak base at the same time. Implies we can say concentration of weak acid is equal to concentration of weak base. Meaning the equation which was derived earlier is applicable. The pH is going to be equal to half into pKw plus pKa minus pKb. This equation now applies completely. So we can now apply this equation straight away. So if I apply this equation, what will I be getting? I will be having pH of HCO3 minus. Now what is HCO3 minus? I can now pair it with some kind of spectator ion, meaning I can write this as pH of NaHCO3. Only any concentration. This will be equal to half into pKw plus pKa minus pKb. Correct. So what are each of these things over here? So I'm going to be having the Ka here being nothing but Ka of HCO3 minus, which is Ka2. Correct. So this is Ka of HCO3 minus, which can be effectively written as Ka2 of H2CO3. And lastly, of course, the Kb here can be written as Kb of conjugate base, which of course is going to be Kw by Ka1 of H2CO3. So if I now apply this setup over here, what will I be getting? This is going to be equal to straight away half into pKw plus pKa2 minus, it is going to be P of Kw by Ka1. So minus P of Kw by Ka1. Meaning I can of course write this as half into pKw plus pKa2 minus pKw plus pKa1. Meaning I will now have pKw and pKw cancelling out. So we will have pH of NaHCO3, any concentration, NaHCO3 only present in solution, any concentration working out as half into pKa1 of H2CO3 plus pKa2 of H2CO3. The same thing can be extrapolated for any middle salt. In the sense, if I have say H6A, first this will become H5A minus, then this will become H4A minus 2 and dot dot dot. So if I want for this fellow here, this will be Ka1, this will be Ka2. For this, the next will be Ka3. So if I want the pH of this fellow, middle fellow here, what will it be? It will be previous and next. So it will be Ka2 over here. So it is going to be half into pKa2 plus pKa3. Just like how for this one is the one we calculated for now. So this one was half into pKa1 plus pKa2. Same way for each of the middle fellows, you can proceed on and calculate over here. I'll come back and discuss this tomorrow in another example. This salt of weak acid, weak base, by the way, behaves like a buffer. We will continue on with buffers and close off with buffers. There's one more small bit in buffer to discuss. So buffers, indicators and KSP is left. I'll close it off tomorrow. We will shut today for now. It's been the 15 to 20 minutes bhi ho gaya hai. So we'll shut today's session here. Any doubts in today's discussion, dude?
No, sir. Everything is
So
clear.
now you will have to basically practice. This is more or less a quick blast through because you have learned this once before and you have learned it decently well, I'm assuming. Huh. Start working on questions when you have time.
Yes, sir. I'll try.
Okay, all right. Take care then. Bye bye. I'll see you tomorrow. Tomorrow you're available, or what is your situation like?
Yes, I'm available.
You want to have a class tomorrow morning also?
Sure, sir. I mean, if you're fine with it.
I am available. I don't have much to do in the morning tomorrow. But yeah, you're having continuous classes. If you're okay with it, I'm perfectly fine with it. So I suppose I'll see you tomorrow morning then. Bye bye.
Okay, sir. Thank you, sir.
Similar timing, 7:30 ko just message me. We'll fix up a timing. Mostly 8ish probably.
Yes, sir. Sure.
Bye dude.
Bye.
Have a nice day. Happy Pongal.
Thank you, sir. Happy Pongal.